Well, welcome back, everybody, to the penultimate video in this Chemistry 1030 series. Today, we are going to be focusing on acids and bases, and what you're going to find as we continue through this work today is that acids and bases play a very, very important role inside of the body for biochemistry purposes, for blood purposes. When you go down the list, acids and bases are very, very important to us as chemists. They're very important to biologists, doctors, etc. So we're really going to spend some time breaking down why these are important and what acids and bases are and the different types of functions that we can do with this information. So very excited to have you along today. We will go ahead and get started with the objectives, and boy, do they look long, but we'll try to get this done in an hour just like we always do. I want you to be able to define what an acid and base is, distinguish between the terms ionization and dissociation, define an acid and base using Bronsted-Lowry method, recognize conjugate acid-base pairs, know characteristics that define what's called an amphoteric substance, differentiate among mono, di, and triprotic acids, write chemical reactions that show the transfer of protons, know the classifications for strong and weak acids and bases, know the chemical formulas for those as well, understand how the ion product constant for water is obtained. It's a little bit of a fancy term there. And then a lot of calculations about the H plus concentration, OH minus concentration, pH, POH. We'll talk a little bit about pKa and how that's used to determine whether something is acidic or basic, and then talk a little bit about buffers and buffer solutions today. So I'm really excited to have you along for today. Should be a good video. As always, if you are interested in more, feel free to like and subscribe, and let's get going on. So first thing we're going to do is just simply define some acids and bases, and you're probably quite familiar with acids and bases in your everyday life. You may have just not realized that the substances that you're looking at are acids and bases. They're very commonly used in the medical field. So for example, gastric juice is made up of hydrochloric acid. That is the juices that are inside your stomach that help you break down foods and break down macromolecules into smaller substances that the body can absorb and then use for cellular functions and whatnot. Lactic acid builds up in the body when you do not take in enough oxygen. That's like the pain that you feel if you go running and haven't done any physical activity for a while. You kind of feel that cramping as you try to get some physical activity in, and that's lactic acid that's building up because your body's not taking in enough oxygen to be able to convert what's called pyruvate. The pyruvate that would go inside of your mitochondria for the process of cellular respiration can't do so without oxygen to be able to perform the rest of cellular respiration. So what happens is it's converted into lactic acid, and the body can't really do much with it, and so it burns and stings and that type of stuff. And that hurts. And common soaps use sodium hydroxide, which is a strong base that helps get your hands clean, all that kind of stuff. You see on the right-hand side here, you see a lovely salad with a vinaigrette dressing on it. Vinegar is acetic acid, which, based on the name, is an acid in and of itself. So you experience and see a lot of acids in your everyday life. So how do we define what is an acid and what is a base? Well, in 1884, the Swedish chemist Svante August Arrhenius proposed that acids and bases are defined by the chemicals in which they form when they are dissolved in water. So one of the most basic definitions of acids and bases is the fact that acids are compounds that will produce hydrogen ions when you put them into solution. So for example, if I take HNO3 and I put it into water, it will dissociate. It will break down into its ions of H plus and NO3 minus. The fact that it gives off that H plus ion is an indication that this is an acid. HCl is another example. When we put HCl into water, it breaks down into H plus and Cl minus. The exact same process occurs. We get an H plus ion as a result of that. Bases, however, are compounds that produce hydroxide ions. So for example, KOH, if you were to put it into water, will dissociate into K plus and OH minus ions, the OH minus being the hydroxide ion. And it's the same with NaOH. It will dissociate into Na plus and OH minus. Now, I use the term dissociation a lot when I describe acids and bases, and I tend to use it uniformly, and I suppose I probably don't use it correctly. But the term ionization is best when referring to acids and how they dissociate, because they don't originally have ions in them. So acids technically ionize, that is, they become ions or produce ions when they're put into solution. Bases, however, for the example, the ones that you have on the right-hand side, if you have a metal hydroxide, it's going to dissociate. Those ions are initially present because a KOH, NaOH, that is an ionic bond. It is a metal plus a non-metal. So I probably won't quiz over the difference between ionization and dissociation. Like I said, I tend to use the terms interchangeably, so it's really nothing that you have to worry about, but you may see different individuals use these in different terminologies. I'll probably just use the term dissociation because it's breaking apart and ions are left over at the very end. To me, what it starts with is fairly irrelevant because we're trying to figure out what's produced afterwards. So that being said, I'll probably use the term dissociation more often than not. And as you kind of mentioned before, acids are covalent compounds that undergo ionization when placed in water. The process is that positive and negative ions are produced from a molecular compound dissolved in solution. So the reason we use the term ionization is that they don't start as ions, they become ions after the process. Some properties of acids are a sour taste, things like sour gummy worms, lemons, limes, citrus fruits, those types of things. Because they contain citric acid, the sweets that have the coating on the outside, that can be citric acid or malic acid. They have a sour taste associated with it. If you've ever used litmus paper before, it turns litmus paper red, and acids can be quite corrosive. They can be quite dangerous. It's one of the reasons why, not to sound too gross and disgusting, but after one vomits, they should immediately brush their teeth because the hydrochloric acid that's in your stomach is very, very corrosive and can damage the enamel on your teeth. So got to be extra careful there. Bases, however, are ionic compounds that undergo dissociation when placed in water. Now, again, these are the bases based off of the Arrhenius definition, but it's a process in which positive and negative ions are produced from an ionic compound. So these are already ions because ionic compounds are made up of, ions, and it's a metal plus a nonmetal. These tend to taste very bitter. If you've ever had your mouth washed out with soap when you were a kid, it was a common thing back when I was young. But they have very, very bitter tasting. They turn litmus paper to blue, and they're very, very slippery to the touch. So I would make sure you know some basic properties about acids and bases. Now I have a video here from Nile Red, not a sponsor, not going to show you the video entirely. Might actually demonetize the video. But this is what happens when you take a very, very strong acid. I believe it's actually piranha solution. If I remember, piranha solution is, correct me if I'm wrong, I think it's hydrogen peroxide and sulfuric acid. I can't remember which acid they use, but the hydrogen peroxide acts as a very, very strong oxidizer, which literally just eats through this entire thing, and then the acid just kind of does what acids normally do and is corrosive. So I'm not going to show you this entire video by any stretch of the imagination. You can watch it on your own if you want. I'd say link in the description, but so while we have a very basic definition of acids and bases, there's a more comprehensive definition that I want us to look at, and that is the Bronsted-Lowry acid-base theory. And the Bronsted-Lowry acid doesn't really change much from the original definition of an acid. The original definition of an acid was that they were hydrogen ion donors. They give off H+ ions. So a Bronsted-Lowry acid is a substance that can donate an H+. That really didn't change terribly much. But a Bronsted-Lowry base is a substance that can accept an H+, so it doesn't have to necessarily have OH at the end of it. Hydrogen ions don't exist in their free states, so very often I will react them with water and produce what are called H3O+ ions. I want to be very clear. When I refer to H+, H3O+, it really does mean the same thing. It just depends on who you're talking to. I prefer H3O+, just because I teach AP chemistry, and that's kind of what the College Board has leaned to over the last couple of years. So if I look at HCl and its reaction with H2O, the HCl is going to donate its hydrogen to the H3O+. So you can see a transfer of hydrogen that's here. The H leaves the HCl and is donated to the H2O. So that makes HCl the acid and makes H2O here a base. And you can see that on the product side. H2O has become H3O+, while HCl has become Cl-. So the HCl has lost its hydrogen, or donated it, and H2O has accepted the hydrogen, which is why you see it attached to H2O on the product side. Remember that H3O+ is what we're looking for when we're trying to define if something is going to produce an acid or a base. So as I mentioned before, let's consider that last reaction of HCl with H2O. HCl is going to behave as an acid as it donates a hydrogen to H2O, and H2O is going to act as a base. It accepts the hydrogen from HCl. So it's pretty easy to see where the hydrogen is being transferred from and where it's being transferred to, and that helps you identify what is behaving as the acid and what's behaving as a base in that particular chemical reaction. Just look at where the hydrogen starts, where it ends, look at where it comes from and where it goes to, and that will help you figure out which is behaving as the acid and which is behaving as the base. Now, many acid-base reactions don't go to completion and are therefore in an equilibrium state. So you notice here you have the double arrow indicating that not all of the HF and H2O become H3O plus and F minus. These typically happen with things that are called weak acids and bases. Strong acids and bases essentially dissociate to completion, but we'll explore a little bit more later on about whether this, or we can determine if this is in an equilibrium state or if it's not in an equilibrium state. But I just want to make sure that you're aware that sometimes you might see the single arrow and sometimes you might see the double arrow. Just don't let it fool you. We're still referring to acid-base reactions through this entire unit. Now, one thing I want you to notice is that there are some terms that we use to describe the products of this reaction. So we don't necessarily just focus on the initial acid and the initial base, but rather we take a look at what it becomes at the very end. So I want you to notice that HF is the acid in this reaction and H2O is the base. And I know that because HF donates its hydrogen to the H2O, therefore leaving behind F minus and H3O plus. So the acid in this, which is HF, becomes the conjugate base, which is F minus. And the base, which is H2O here, becomes the conjugate acid on the right-hand side. So acid becomes conjugate base, base becomes conjugate acid, and we refer to these as conjugate acid-base pairs. There's always going to be two of them in each reaction. And they're very easy to identify because they're always going to differ by just a single hydrogen. So notice that the HF and F minus is a conjugate pair. They differ by a single hydrogen, and the H3O plus and the H2O are a conjugate pair as well. They differ by a single hydrogen. Another way to look at this is that the conjugate acid will have always gained a hydrogen, and the conjugate base will have always lost a hydrogen. So if I take a look at the equation again, HF is the acid, the conjugate base has lost a hydrogen, and so that's why F minus is your conjugate base. The H2O has become H3O plus, which means that the H2O has gained an gained a hydrogen rather, and so therefore the base, which is H2O, has become the conjugate acid on the right-hand side. Okay, so what I'd like to do, I was originally going to do just a little bit of practice with this, but you could take a look at all of these that are here, and it's pretty straightforward. You can figure out what the acid is, conjugate base. You notice that all of them on the left-hand side, the acid has a hydrogen in it, and on the right-hand side, it has lost the hydrogen. So the acid has become the conjugate base. Now, a couple of these, you'll notice that the hydrogen does not necessarily start the molecule that we're looking at, or the compound that we're looking at. Sometimes it occurs at the end. A lot of times you see this with organic acids. Regardless of where the hydrogen is that's gained or lost, you should be able to identify which is the acid, which is the conjugate base, based on how it changes over the course of the chemical reaction. In addition to that, you can see that the bases become conjugate acids when they have gained a hydrogen. And again, it doesn't really matter where that hydrogen is being gained at. Most often, organic bases, such as the CH3NH2, the hydrogen is going to be added at the very end there. You notice that it's lost in the organic acid, the CH3COOH, on the left-hand side. So just a couple of things to think in mind. Just a couple things to keep in mind about acids, bases, and their conjugates. Take a look very closely at what has donated its hydrogen and what has accepted the hydrogens as you go through and observe. So based off of that information, I'd like you to determine the chemical formula for each of the following, thinking about whether it is going to have gained a hydrogen or lost a hydrogen based on the information we just discussed. Take a few moments, we'll come back, and we will answer these questions in just a moment. All right, so I've given you a minute to kind of think about things. Well, maybe not a minute in real time, but you get the idea here. So we were asked to find the conjugate base of HSO4 minus. So if we're searching for the base, then we're going to make the assumption that this is the acid. And remember that acids donate their hydrogens, so we're going to lose a hydrogen off of this. So the conjugate base of this is going to be SO4. And then keep track of your charge. Remember that when we lose hydrogen ions, we lose a positive charge. So that makes SO4 more negative by 1. So it's going to be SO4 2 minus. I want the conjugate acid of NO3 minus. So this is the base. So what we're going to do is we are going to add a hydrogen. Again, keep track of your charge as you do this. Positive and negative will cancel. So the answer to this is going to be HNO3. Just like that. We want the conjugate base of H3PO4. So again, this is going to behave as an acid. So it's going to lose a hydrogen. So we end up with H2PO4, and that's going to have a minus charge on it. And the last thing was the conjugate acid of HC2O4 minus. So we are going to gain a hydrogen here. So this will be H2C2O4 and with no charge on it. So again, just make sure you keep track of what's an acid, what's a base, conjugate acid, conjugate base. Remember that if we're looking for the conjugate base, the first part's going to behave as an acid. And as long as you can think of those things, you'll be in good shape here. Also, make sure to keep track of your charges as you continue to move forward with all of this. We'll see you very, very soon. So there are a few molecules that you need to consider that can behave as either an acid or a base. Now that's going to be depending upon what substance you react them with. And we refer to these substances as amphoteric substances. Basically just means that they can behave as an acid or a base. So take a look at the reaction below. So we have HNO3 plus H2O yields H3O plus and NO3 minus. So in this case, the HNO3 is behaving as the acid, which means that the H2O is going to behave as the base. And then that means that the H3O plus will be the conjugate acid and the NO3 minus will be the conjugate base. So here, water is behaving as a base. Underneath that, we have NH3 plus H2O yielding OH minus and NH4 plus. So in this case, the water is the one donating the hydrogen. So in this instance, it's behaving as the acid while the NH3 is behaving as the base. The H2O as an acid will become OH minus, which is the conjugate base, and the NH3, which is the base, becomes the conjugate acid, which is NH4 plus. So you really need to just pay close attention to the chemicals themselves. Sometimes based off of its chemical formula, you can tell if it's an acid or base, but sometimes you can't. So take into consideration what it's reacting with, take a look at the whole equation, and that will help you get a better indication of whether you're dealing with an acid or a base. So here is just a list of summaries for you, so that way you can kind of keep track of all of this information. It's from the textbook. It provides pretty good explanation as to the difference between acids and bases and how we identify which is an acid, which is a base, etc. You can feel free to pause the video and look at that on your own time if you wish to do so. Now, we can further distinguish acids based off of the number of hydrogens that are available for donation, and these use some prefixes that are pretty familiar to all of us. A monoprotic acid is an acid that can supply one proton. A diprotic acid is one that can supply two protons, such as H2SO4, the monoprotic acid being HCl. And then a triprotic acid is one that can give three protons. So H3PO4 would be an example of this. Be aware that the number of protons or the number of hydrogens that can be donated does not correlate to the strength of the acid. That is something we will address here in just a moment. But don't think that a triprotic acid, because it has three hydrogens, is going to be a stronger acid than a monoprotic acid, which just simply has one. And any acid that has the ability to give more than one hydrogen is known as a polyprotic acid. So pretty straightforward to distinguish between your mono, di, and triprotic acids. Now, the relative strength of an acid is going to depend on how much it dissociates into its ions. All right, the strength of an acid is not correlated to how quote-unquote dangerous it is or how many hydrogens are available on the molecule before it dissociates. It just simply matters how much of it dissociates. A strong acid is one where 100% of the compound transfers its hydrogen ions. And if we think about equilibrium, right? If all of my reactant becomes product, well, that tells me that equilibrium lies really far to the right because we have a significant higher number of products than we do reactants. A weak acid is one where a small percentage of the compound dissociates and transfers into its ions. So you can consider that to be one that does not produce a lot of H+, and as a result, the equilibrium position lies really, really far to the left. So the strength of an acid, and if we look at the diagram on the right-hand side, the strength of an acid depends on how much H3O plus we get from it once it reacts. If you notice that the strong acid, we have lots of H3O plus and very little of the original acid, which is denoted as HA. If I look at the weak acid, we still have a lot of HA left over after equilibrium has been established. So the relative strength of an acid is not based off how many hydrogens it starts with. It's solely based on how much H plus or H3O plus we get after the dissociation occurs. Now, here's a list of strong acids and bases. These are ones you're just going to have to know and you're just going to have to memorize. We have HCl, which is hydrochloric acid, HBr, which is hydrobromic acid, and HI, which is hydriodic acid. You then have nitric acid, chloric acid, perchloric acid, and sulfuric acid. So these are the ones that readily get rid of that hydrogen. In addition to that, we have some commonly encountered strong bases. These are all OHs. These are all hydroxides. And it's all of the hydroxides in group 1 plus calcium, strontium, and barium. So These are just things you're just going to have to memorize, unfortunately. There's really no other way around it. There's no periodic trend. Well, there are some periodic trends that are related to the strength of acids, but that is beyond the scope and sequence of this course. But what I'm trying to get at here is that you're just going to need to go through and memorize these lists. So this is definitely a concept that goes above and beyond this course, but it helps explain an equation that we're going to look at here. And although water is a covalent substance, a very small amount of it will react with each other to transfer protons. So water mixing in and of itself can behave as an acid or a base. It's referred to as self-ionization, and very small amounts of H3O plus and OH minus are produced from this. So in this case, water is acting as an acid and the other water molecule is behaving as a base. And we get an H3O plus and OH minus from this. Now, I want you to keep in mind that every time water does this, we get one H3O plus and one OH minus from this. So the amount of H3O plus and OH minus will always remain equal to each other, right? You're not going to have one above the other because every time water does this, it produces one of each of these things. And a very small amount of H3O plus and OH minus are produced from this process. In fact, it's 1 times 10 to the negative 7th for each. So it's a very, 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 very small amount of H3O plus and OH minus that are produced from this. But because very little of this becomes product, we're in an equilibrium expression. And because we're in an equilibrium situation, we can write that expression for it. So if I go back, water and water are liquids, and we never include liquids in equilibrium expression. So that means that Kw equals H3O plus times OH minus. And using the values from the previous slide, we can determine that Kw is 1 times 10 to the negative 14th, right? If I take 1 times 10 to the negative 7th for H3O plus and 1 times 10 to the negative 7th for OH minus, I multiply them together and get 1 times 10 to the negative 14th. What's nice about this is that this equation not only reacts or works for water, but it can be used to calculate the concentration for any ions present in these solutions. We simply plug in one for the other and we can solve algebraically for these. Now, that negative 14 number might look awfully familiar to you if you are familiar with the pH scale. You might know that the pH scale runs from 0 to 14. And that's actually where the 14 comes from, is this auto-ionization constant of water. So based off of this formula, we can do some calculations and determine how much H3O plus and how much OH minus we get from this. And then we'll evaluate what that information means a little bit later on. But for right now, what I'd like you to do is I'd like you to go through and try to do some calculations with this. We'll walk you through it step by step here in just a moment. But remember, we have that formula, Kw equals H3O plus times OH minus. Remember that Kw is 1 times 10 to the negative 14th, so just plug some numbers in and algebraically solve for the unknown concentration that's listed here. We'll bring it back in just a moment. All right, so we're going to go ahead and solve for this. I got out my handy-dandy little calculator to help us out, but let's go through and see what we can do to calculate these out. Now, let's remember our equation here. So we have Kw equals 1 times 10 to the negative 14th, and Kw equals H3O plus, stylus is not behaving today, times OH minus. So it simply becomes a plug and chug algebra problem. So we're going to take 1 times 10 to the negative 14th. That is equal to, I'm given an H3O plus, which is 4.0 times 10 to the negative third. And we multiply that by OH minus. And then again, we just do a little bit of algebra here. So what we're going to do is we're going to take 1 times 10 to the negative 14th, and we're going to divide that by 4 times 10 to the negative third. If you need to, put it in parentheses, like I forgot to do. And so what we get here is our OH minus equals 2.5 times 10 to the negative 12th. Okay. These are concentrations, so we are going to use M to describe them. Or the OH in brackets also describes concentration as well. We're going to apply the same exact concepts to the problem down here below. So we're going to take 1 times 10 to the negative 14th. We need to find H3O plus, that is our unknown. And we're going to plug in our OH minus. So 1.2 times 10 to the negative 9th. And we're just going to algebraically solve for that like we just did. So 1 times 10 to the negative 14th divided by 1.2 times 10 to the negative ninth. Again, parentheses, please. And what we get is 8.3 times 10 to the negative 6. Sorry, my calculator was not in scientific notation, so I actually had to think about it. And that is equal to my H3O plus. Okay. Now, these numbers don't mean a whole lot to you at this point in time. That's what the next slide is going to show you. It's going to tell us that the relative amounts of these materials is going to tell us whether the solution is going to be acidic or basic. I will bring you back in just a moment and show you how to go through and do that. So why do we go through and calculate H3O plus and OH minus? Well, it's a way for us to be able to determine that if it's... So what's the reason why we go through and calculate H3O plus and OH minus? Well, that information helps us determine if a solution is going to be acidic or neutral. An acidic solution will have an H3O plus concentration that is higher than that of OH minus. And a basic solution is going to have an OH minus that is higher than that of H3O plus, and a neutral solution will contain the same of each. So the graphs here are a little bit confusing, all right? But the further you go down, the more concentrated it is. It's a little bit difficult to interpret here, but the very first solution you have is a neutral solution where we have equal amounts of H3O plus and OH minus, just like what we discussed before. Those will be 1 times 10 to the negative 7th for each of them. As we add H3O plus, we actually eliminate OH minus. So as the H3O plus concentration increases, OH goes down. H3O plus is in greater concentration than OH minus, so the solution is acidic. And the opposite's true. If we end up with more OH minus, that means that H3O plus decreases. We have more OH minus, so it is a base. So go back and take a look at the previous couple of problems and think to yourself, is this base solution acidic? Is this solution basic? Is it neutral? Remember, compare the relative amounts of them, and remember that your exponents are negative. So keep that in mind as you go through and evaluate those. And this might be a little bit better way to examine the relationship here. You look at the chart down at the bottom, a little bit easier to interpret here. A neutral solution is where H3O plus and OH minus are equivalent to each other. An acidic solution is where H3O plus is greater than OH minus, and basic is where OH minus is greater than H3O plus. So again, just another way to visualize the information that we've just taken a look at and that we've just covered. Now, as non-scientists, or as many of us are non-scientists just out in the real world, it's inconvenient to work with those numbers. You don't go to somebody at the pool store and go, oh, well, your H3O plus concentration is 1 times 10 to the negative 5th. You need to add a little bit of base to it. First off, you're going to get punched in the face. And second, you're probably going to get called a nerd. For some people, that's a compliment, like me. But anyways, we simplify this information by using what's called the pH scale, which is a much easier way, it's a much more simplistic way to determine if something's acidic or basic. Basically, to determine the pH, you need to take the negative log of H3O plus. And so this actually makes this scaling a little bit different. With the pH scale, it's a log-based scale. And logs are what are called base 10, which means that the difference of a pH of 1 is actually a difference in 10 times the acidity. So for example, something that has a pH of 2 compared to something that has a pH of 3, well, the one that's 2 is 10 times more acidic than the one with the pH of 3. We'll examine the pH scale in just a moment to determine if something's acidic, basic, or neutral, but for now, I'd like you to go through and calculate the pH of the following solutions, giving the H3O plus concentration. So just simply take the negative log of these values, and you will get the pH, and then we'll take a look in just a couple moments to determine if they are acidic or basic. Be back with you here in just a couple moments. All right, so here we're given a couple of different concentrations of H3O plus, and we're trying to determine the pH of these solutions. So we'll do a little bit of help with this. If the pH is less than 7, it is an acid. If the pH is greater than 7, it is a base. And if the pH is 7, we'll call it neutral, okay? Just to kind of give us an idea. So we're just gonna plug these into our calculator and solve. So this is actually very easy to do. So negative log, and then I'm going to type 6.3 times 10 to the negative 5th, and I get 4.20, or 4.2 if we use proper sig figs. This would be an acidic solution because it is less than 7. So do the same thing again. In fact, what I'm going to do is I'm just going to change the number. No, I'm not. I'm going to just type it in again because that's actually easier. So take the negative log of 5.3 times 10 to the negative 5th. We get 4.3, still an acid. And then here, 2.2, oops, negative log. Follow your own directions, Joe. Seriously. You're trying to help people here. 4.7. So all these are acids. Okay, but again, the numbers there are much easier to interpret than, say, the exponents that are available. All right, let's move on. So now we want to do the inverse function with this. This isn't something that I've gone through and discussed right away, but what you'll notice is that a lot of times on your calculator, the inverse function is just the secondary function of the button that I pressed. So I'm looking at my calculator right now. And the log button, the secondary function of that is 10 to the power of. So if I want to go the reverse direction and solve for H3O plus, you're going to take 10 and raise it to the negative pH. It's a pretty simple way to go through and solve for some of this, but again, we're just looking at going the reverse direction here. So if I want to do this first one here, I'm just going to calculate the H3O plus. (10 to the negative 1.2). And I'm going to do that for all three of them. So take a moment, go through, calculate those. We'll be back in just a moment and calculate the rest of these. So go ahead and calculate the first one, which is going to be 6.3 times 10 to the negative second. Remember that these are concentrations, so molarity of H3O plus. So off to a good start. Let's do that with negative 6.9. So what we end up with here is 1.3 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. I think it's negative 7th. Then lastly, we do it for negative 10.4. Much easier there. We get 4.0 times 10 to the negative 11th. So again, just a couple of easy ways to go through and do some calculations with these pH numbers. Just make sure you have the ability and flexibility to work back and forth between the different formulas that we've looked at. We've looked at three, right? Kw equals H3O plus times OH minus. The negative log of H3O plus equals pH. And then 10 to the negative pH will equal your H3O plus, right? Let's move on and keep working. So as I mentioned previously, and we'll keep taking a look at this moving forward, an acidic solution, it has a pH that is less than 7. A basic solution has a pH that is greater than 7, and a neutral solution has a pH that's equal to that of 7. So much easier to determine if something's acidic, basic, or neutral based off of the pH scale. And again, keep in mind that each number on the pH scale is base 10, meaning that let's say we look at something with a pH of 1. Something with a pH of 1 is 10 times more acidic than something with a pH of 2. Something with a pH of 1 is 100 times more acidic than something with a pH of 3. They're multiplicative as you work through them. So again, just a couple of things to think about. Oh my goodness, it's like I just mentioned this. I forgot this was a slide that was coming up, but reiterate the point that I last made. It is a log-based scale. So a solution that has a pH of 1 is 10 times more acidic than with a pH of 2. A solution that has a pH of 1 is 100 times more acidic with a pH of 3, and so on. So multiplied by 10, and they're multiplicative. So something to just kind of keep in mind. Here are some common liquids and various pHs that are on some living tissue here. So battery acid, acid cleaning products have a pH of less than 1. They're very acidic, can be very damaging to living tissue. Gastric juice has a pH of 1 or 2, can be very irritating. Citrus juices and vinegar, those have a pH range of 2 to 5. They can be irritating to mucous membranes. Don't be snorting citric juice. 5 to 8 is usually pretty non-hazardous. Cola drinks, coffee, tap water, intestinal fluids, urine, etc. You start going up the scale, you get more basic. These can be a little bit more harsh. Seawater, soap, you get soap in your eyes, it's pretty painful. Household ammonia and bleach, and then oven cleaner, drain cleaner, very, very hazardous. So most people just have this notion that acids are the only ones that are dangerous, and that's not true. In fact, bases can be quite as dangerous, if not more dangerous than acids sometimes, because most people don't think of bases as being toxic or dangerous to human health, but in fact, they quite are. And here's a table that just shows some normal pH range of select body fluids. I want you to notice very closely blood plasma, very, very strict range of pH, because you can have some very, very serious medical issues, things like ketoacidosis and whatnot, if you have a blood pH that is outside of that range. So just some things to keep in mind. Now, when dealing with a specific chemical, we need to know first off whether it's an acid or base. So I'm not always just going to give you, hey, this is the concentration of H3O plus, hey, this is the concentration of OH minus, to go through and calculate it. What I am going to tell you is this is a concentration of an acid, this is a concentration of a base. Now, when we do this, we're only going to be dealing with strong acids and bases, so it makes it a little bit easier. So for example, if I give you a chemical that is an acid, that's the same as the concentration of the H3O plus, and then you do your negative log accordingly. If it's the concentration of a base, it's the concentration of OH minus, you'll have to do a little work to get the H3O plus and then calculate the negative log from there. Again, think about the variety of different equations that you have as you go through and work through some of these problems. All right, so kind of the last big topic we're going to go through and cover are what are known as buffer solutions. Now, buffers are aqueous solutions that prevent substantial changes in pH. And that's very, very important because, like we've mentioned before, the human blood has a very narrow range of pH. It has to be heavily buffered to prevent changes in pH because that keeps oxygen transport optimal if we have a pH range somewhere between 7.3 and 7.5. So in order to be a buffer, we have to have two things. We must have a weak acid or base and its conjugate. Now, often the conjugate base is given as a soluble salt of the conjugate base. So, for example, HCN, we know is not one of our 7 strong acids, but sometimes what we'll give is a salt that's associated with it. So if I were to add in the conjugate base, I don't just have CN minus ions just hanging around, so I add some potassium cyanide, and that gives me my CN minus ions. So it has to include something that's weak and its conjugate in order for it to be considered a buffer solution. Remember that conjugate acids and bases only differ by a single hydrogen as you go through and take a look at some of these practice problems. So what I'd like you to do is take a few minutes and determine if the following would work as a buffer solution. Remember, we need to have an acid and its conjugate base. And furthermore, it needs to be a weak acid as well. So keep that in mind as you go through and evaluate these, and then we will move on here in just a moment. Well, I didn't mean to jump ahead and go through and do all of this before you got a chance to kind of do it along with me. However, I realized I went through and did all of this, and yeah, I was not recording. So I have done all of the work and mentioned all of the things without recording. So let's look at this individually and break this down. So for A, remember when we go through and do this, we need to make sure that we have a weak acid or base and its conjugate. And if we look at HCl and NaCl, remember that we can disguise our conjugates as ionic compounds. Remember that NaCl will dissociate, so we'll get Cl minus out of that. So what we end up with in solution is HCl and Cl minus. Albeit this is an acid-base conjugate pair, HCl is strong, so this is not a buffer solution. HCN and KCN. KCN produces cyanide minus ions, so that gives us HCN and CN minus. They are a conjugate acid-base pair because they differ by a hydrogen, and HCN is weak, so that is a conjugate acid-base pair. And then the last one there, the third one there, is acetic acid, HC2H3O2, and sodium acetate, NaC2H3O2. That will dissociate and produce C2H3O2 minus ions, so we end up with HC2H3O2 and C2H3O2. That is a conjugate acid-base pair, and it's a weak acid, so that would be considered a buffer solution. And then lastly, we have NaCN and KCN, and there's no acid there. And when we don't have an acid, we don't have a buffer. So again, pretty easy to determine if we have a buffer solution. We just need to look at our chemicals that we have available. First off, we have to ask ourselves, do we have a strong or weak? We have to ask ourselves, do we have a weak acid or base? Do we have its conjugate? And if so, then we can be considered a buffer solution. So that being said, I will try to remember to hit record for this before I start yapping away. Let's move on. So this slide here really drives home the importance of buffer solutions inside of the body. As we mentioned before, the pH range of blood is very, very narrow, in this case between 7.45 and 7.35. If we just differ ever so slightly from that, we end up with what's called alkalosis, which is a blood solution that's too basic, and acidosis, which is a solution that is too acidic. And you even deviate a little bit further from that, and the individual can no longer survive. The oxygen-rich environment of the blood no longer functions the way it's supposed to, and as a result, person's dead. So buffer solution is very, very important. And what they use in the blood is what's called carbonic acid. It's H2CO3 and HCO3 minus, and that acts as your buffer solution. But how do buffer solutions work to mitigate changes in pH? Well, let's take a look and see how they work. So let's consider the HCN-KCN buffer solution that we've taken a look at previously. If we add an acid, it will react with the base in the buffer. So if we think about what makes an acid, it's the H3O plus. So you notice how I am reacting this. So H3O plus gets put into the solution and it reacts with the conjugate base, which is the Cn minus. Acid will donate its hydrogen to the base. And so what you end up with is HCN and H2O. So my products no longer have the H3O plus in it. Remember, it's the H3O plus that makes the solution acidic and the OH minus that makes the solution basic. So as a result, we've mitigated the acid that's in the solution. And what we've actually created is the conjugate acid that's already in our buffer solution. We're creating HCN, which is a part of the buffer solution in and of itself. Adding in a base will react with the acid in the buffer solution. So if we add in something that produces OH minus ions, it's going to react with the HCN, and the HCN is going to act as an acid and donate its hydrogen to the OH minus, resulting in H2O and Cn minus. So you notice that regardless of whether we add something that is acidic or basic, the opposite of it will react and it will produce water and then the other component that is part of the buffer solution. So when an acid reacts in the buffer solution, we get HCN and H2O, water. When a base reacts, we get Cn minus and H2O, which is water. Pretty neat, isn't it? So again, as we figure this out and we figure out what we need to write, we need to consider, okay, are we putting in an acid or are we putting in a base? If we're putting in an acid, H3O plus is going to be one of our reactants. It's going to react with the base. If we're adding in a base, then OH minus is going to react, and we're going to react that with the HCN. Both will produce water and the opposite component that is a part of the buffer solution. Let's see how that works here in just a moment. So here what I'd like you to do is I'd like you to write an equation for each of the following buffering actions in these solutions. So what happens when we add H3O plus to an HFF minus buffer solution, and then when we add OH minus to a carbonic acid solution and a phosphoric acid solution? Take a few moments, think about it, and we'll be bringing you back in just a moment. All right, so as we go through and finish this up today, again, we have our buffer solutions here. We know these are buffer solutions because these are weak acids and bases and their conjugates, which is fine. But as we write these out and figure out how to write out buffer neutralization reactions, we need to first take a look here. We're adding an H3O plus, so we're adding an acid. So remember that the acid is going to react with the base that's in the solution. So when I start writing this out, I write H3O plus. They're all aqueous except for water. It's going to react with the F minus, which is also aqueous. When this happens, we end up with a transfer of hydrogen from the H3O plus to the F minus. And so what we end up with, as we talked about before, is water, because the H3O plus is going to lose a hydrogen. And then the hydrogen is going to get transferred to the F to make HF. So again, notice I neutralize the H3O plus by producing H2O and F minus. Quite convenient. This one is a base, so it's going to be reacting with the acid in the solution. So we start off with OH minus. It is aqueous. It reacts with the H2CO3, which is also aqueous. And what we get out of this, I should mention we should put double arrows here. These are buffer solutions. Buffer solutions are always in equilibrium, so we use the double arrow here. In this case, the hydrogen is going to transfer from the acid to the base, just like what we described previously. And so what I end up with is H2O, liquid, and H2CO3. Oops, sorry. HCO3 minus, which is aqueous. Okay. For us, we don't need to worry about going back and like balance equations, anything like that. These are already going to be balanced because all we're doing is transferring over hydrogen. So pretty easy to do that. Same thing here. We have a base. It's going to be reacting with the acid. Remember, we only transfer one hydrogen over. Don't transfer them all over. So we start off again with OH minus, which is aqueous. We're going to react that with H3O or H3PO4. Again, that hydrogen ion is going to transfer. So from the H3PO4 to the OH here. And we end up with some H2O, again liquid, and H2PO4 minus. Okay. So again, it's pretty easy to do. You just need to recognize if you're starting with an acid or starting with a base, and then figure out that it's going to react with the opposite component in the buffer solution. You're always going to produce water and the opposite component of what's in the reaction of the buffer solution. So in the first one, we used F- as a reactant. We get HF as a product, both components of the buffer solution. And you see that across the board, all right? A few more things, and I think we will wrap things up in just a little bit. So what I want you to notice is how this mitigates changes in pH. Remember that the amount of H3O plus and OH minus determines how acidic or basic a solution is. So buffer solutions do a really, really good job of preventing that from existing in the solution. Remember that when we add H3O plus, it's going to react with the base in the buffer solution and prevent the H3O plus from changing the pH. And the opposite's true if we're adding in a base. It's going to react with the acid in the buffer solution to prevent OH minus from reacting. But notice that in pure water, if I just add small amounts of OH minus or H3O plus, notice how much the pH changes. Just a 0.01 moles of OH minus can raise the pH of something with a pH that's close to 7 all the way up to a pH of above 12. And we add H3O plus, we can lower it all the way down to 2. But in a buffer solution, notice how very little that changes the solution. So buffer solutions do a great job. Now, this isn't going to work infinitely. Okay, a buffer solution is only as good as how much of the buffer solution you have or how concentrated the buffer solution is. You can eventually run out of acid or base to react with, and then you do see large changes in pH. So the amount that the buffer has the ability to mitigate is dependent upon its concentration. A story for another day. Another way that we can look at relative strengths of acids is by looking at what's called the pKa. We won't spend a lot of time talking about pKa. It's the negative log of a Ka value. K is an equilibrium constant for an acid. You don't have to worry about it much. Just the lower the pKa, the stronger the acid. Very similar to how you think of pH. The lower the pH, the stronger the acid. The lower the pKa, the stronger the acid as well. And so lastly for this unit, and there will be other things that I add, I'm actually going to go through and rearrange this a little bit later on, but we can calculate the pH of a buffer solution by using the Henderson-Hasselbalch equation. This is where the pH of the buffer solution equals the pKa of the acid. I'll give that to you. And then you just simply need to plug in the concentration of the base and the acid and take the log of that, and that will indicate whether or not the pH is slightly above or below the pKa. You need to think about this as well, is that if I have a pKa value, which is representative of how strong an acid or base is. If there's a little more base than acid, that should cause the pH to be a little bit higher than the pKa value because you have more base, right? More base in the solution means that the pH should be higher. And if we add in more acid, then the pH will be a little bit lower than the pKa. So you can use this as a way to really think about, did I go through and do this math correctly? So we got one more practice problem, and then we will be finished. So being finished, here's the last practice problem. I give you some concentrations of some acids and some bases. It asks you to calculate the pH of the buffer solution. Do that, and we will be done and finished. We'll see you here in just a moment. All right, so the very last problem here, it does ask us to calculate the pH of a buffer solution with 0.01 molar HNO2 and 1.0 molar NO2 minus. So this is the acid in my buffer solution. This is the base in my buffer solution. We're given the pKa, so this just simply becomes an algebra problem. So pH equals your pKa, which is 3.15. Plus the log of the base over concentration of the acid. Now, the base is in higher concentration than that of the acid, so the pH should be a little bit above 3.15, should be a little bit higher than the pKa that's listed here. So let's find out if that's true. So pH is going to equal 3.15. I'm going to simplify this just a little bit. So we'll take 1 divided by 0.01, and we'll take the log of that value, and what we get is 2. All right, so pH is 3.15 plus 2, so that is 5.15. Okay, so does that correlate with what we said up here? It sure does. The pH is slightly higher than that. Yeah, quite a bit higher because this is a very vast difference in concentrations of acid and conjugate base, but you get the idea here, okay? So this is just, like I said, a quick 1-hour overview of the material that we have in chapter number 10. We'll flesh this out more in class, but hopefully you enjoyed that. If you did, like, subscribe, etc. We will see you very soon, and have a fantastic day. Bye, everybody.